there's this thing that we do, and the details vary from language to language. In Ruby, it often looks something like this. You realize that this bit of code over here and that bit of code over there are basically doing the same thing, except they're implemented differently, so you decide to switch everything over to use just one of them. And about 17 tests break, and you remember that there's this one edge case, so you quickly patch a conditional, and now 24 tests are failing, and you realize that there's a missing dependency, and so you pull that in, and you have about 50 failing tests, and it turns out that there's a conflict between two different dependencies. And so you swap them around so that they load in the opposite order, because Ruby, and now almost 80 tests are failing, and then apparently there's an encoding thing that's gone haywire again, assuming UTF-8, but actually getting Latin 1, or is the reverse? I don't know. And the method you're trying to use needs access to some stuff that's not a part of the public API, and so you figure whatever, I'll just use send, and a whole bunch of stuff blows up, and it's something to do with unexpected nils, and it's been hours since the last tests were last passing, and now you're considering monkey patching nil class. And instead, you do a git reset hard. I think every single programmer I know has done some version of this, and not just once, right? We keep doing it. It's as though the fix is right there, within reach. It's so close we can practically taste it. And we chase after it, and our vision narrows, and whatever original plan we had is long forgotten. It's messy, and it's frustrating, and it is massively wasteful. And it doesn't have to be that way. So I'm going to talk about the underlying principles of how to avoid that sort of train wreck. Now, to talk about this, I'm going to use some code that generates a children's song. The song is very simple, but it has an algorithmic component. And this adds just enough complexity to demonstrate real-world refactoring principles without bogging you down in real-world code. The code is in Ruby, but you don't actually have to know any Ruby in order to follow along. Also, don't be distracted by any of the language-specific details. All of that is irrelevant today. The underlying principles are a lot more philosophical than they are technical. So, to start off, the whole code example is all just text. And the code is actually short enough to fit on a single slide. Don't try to read it. I'm just trying to illustrate a starting point for this refactoring. So this is the entire text of the song, and it's hard-coded into a here doc, which is wrapped in a method, and which in turn is wrapped in a class. And that's it. Right? This code is actually pretty nice. Right? It's short. It's extraordinarily easy to read. It does exactly what it needs to do. And you might be wondering how we're going to talk about refactoring when the code is so simple. And that is an excellent question. Usually refactoring is about taking a mess and then cleaning it up, which might make it seem like refactoring is about aesthetics. But fundamentally, refactoring is not about beautiful code. Now, sometimes refactoring could be about comprehension. You might refactor something in order to be able to understand it, but that raises the question, why do you need to understand it in the first place? If you have horrible, awful, terrible, no good code that you don't understand, but it does exactly what you need to do, why bother? Leave it in production, walk away. The right time to refactor is when we need to achieve some practical purpose. Right? You need to make a change. And that change is hard to make the way the code is right now. If we don't refactor, then we're going to end up making the change in some way that's going to cause pain and suffering. And we don't want pain and suffering. So looking at our simple, understandable, perfectly working code, why would we refactor? Well, it turns out the code used to do exactly what we needed. It generates the age-old tale of a little old lady who inexplicably swallows a fly and then compounds the problem by swallowing larger and larger creatures until it kills her. Now, there's been a change in requirements. We want to create variations of the song. It needs to be basically the same song. It's the same algorithm, but we want to be able to generate it with different data. So we need to be able to swap out the original animals with arbitrary creatures. While the code that generates this song is simple and understandable, it's not going to let us do this. So we're going to refactor. You might be tempted to just look at the song and write something from scratch that's going to satisfy the new requirements. That tends to not work quite as well as one would hope. Here's the thing. The code that we have works, and one of the variations that we want is the original version of the song. The code we have contains the correct algorithm. We just need it to be a little bit more flexible. Now, notice that we don't have any tests, and this is for obvious reasons. The code is so simple that there was no point in adding any. But now that we're going to be changing things, we need a quick and reliable way to make sure that we're not heading off into the weeds. So I'm going to make the simplest test that I possibly can by copying the here doc into a brand new test. I'll stick the output in a local variable and assert that this is identical to the generated code, which obviously it is, because right now the expected output is an exact duplicate of the production code. This type of test is called a characterization test. Usually it won't be an exact duplication of your production code, but the main idea is that you're creating a test that asserts that whatever is there is correct. Whatever the code is doing right now is exactly what you want it to continue to do. All right, so we have some code. We need to change it. We have the tests, and so we can do so. The first step of a refactoring is almost always to just look at the code for a little bit, squint at it. Don't worry about reading the details. It's just there so that we can look at the shape. You will very rarely have some blinding insight that will tell you exactly what to do. But very often you'll make some observations about what's hurting your ability to make the change that you need to make. In this case, the most striking thing about this code is that the song is algorithmic, but there is no algorithm apparent in the implementation. At a high level, the algorithm does a couple of things. It tells us how to construct a verse, and it also tells us how to string verses together. So that's not a very fine-grained description, but it does help break down this task into somewhat more manageable pieces. So first, we're going to deal with individual verses, and then we're going to look at how to string them together in the right order. And then once that is done, it should be fairly easy to see what needs to be done to add support for the new requirement. Now, right now, I don't feel like I can actually tackle the first item in the to-do list because the current implementation is just a pile of text, right? There's no way to get at a single verse all on its own because it's all the verses all the time. So before I even start thinking about algorithms and data, I want to break this up a little bit to make individual verses accessible. And for that, I'm going to use a case statement with one branch for each verse. And I'll loop over the range of verses and join them to get the full lyrics. And because I want to be able to focus on the verse all by itself, I'm going to go one step further and extract the case statement into its own method. And this change is a little bit tedious, but it's very quick and straightforward. And we end up with individual verses that look like this. It's lots and lots of strings all concatenated together. So some of this is algorithm, and some of it is data. And the thing that bugs me the most here is that the algorithm and the data are all mixed together. So to get a better idea of what the algorithm actually looks like, I want a better separation of the static and the variable parts. And I'm not really interested in naming anything yet, so I'm going to use the C-style string formatting, which gives a nice delineation with the static stuff on one side and then all the data on the other. And this is a really tiny change, but it's actually noticeable even when you squint at it. This is the here doc that we started out with, and we used a case statement to break up the individual verses with the strings unchanged. And then now we've dissected the strings in place to separate the template from the data. You might argue that I just shoved code around on the slide and pretended to have refactored, the way you might shove food around on a plate and pretend that you've eaten. And it can seem a little bit pointless to make such a tiny change, but the goal was to bring the algorithm into a little bit more focus. And this change actually achieved that. Now there's an algorithmic component that virtually jumps off the page. Each verse grows systematically. It adds repetitions and then it stops abruptly. So I want to explore this a little bit, and I want to do it without risking the code that I know is working. I just want to write down the bit of algorithm that I think is there. I think that I'm seeing this logic, but I'm not going to actually use it anywhere just yet. So what I think I'm seeing is this. Most of the verses take this phrase, and then they repeat it some number of times, passing in a variety of different creatures. And this is not a lot of code, but it seems to be a key element of the algorithm. It seems like a complete thought. When something in the code feels coherent and solid like this, it's worth making an attempt at naming it. Now, this particular part of the song is trying to explain the reasoning behind the little old lady's behavior. It's talking about why she would ever do such a thing as swallow a bird or a dog or a goat. In other words, it's talking about her motivation. So we need to call this method some number of times, each time with different data. And this is another little piece of the algorithm repeating itself, right? Ignore for a moment the fact that cows and goats don't actually eat meat, and notice that the predator in one verse becomes the prey in the next. We essentially have the same list hard-coded twice, but algorithmically, it should be just one list. And this too is a core concept in the song's algorithm. So we should try to give it a name. Now notice the order of the animals here. Right? This is not the order of the verses. The natural order of the algorithm based on how it lives in the code is the order of predation. It's who eats whom. So now our experimental bit of algorithm looks like this. It takes two concepts that we've already named, critters and motivation, and it combines them into a bigger story. All of these critters are taking part in some larger drama where each successive iteration through the loop intensifies and exaggerates this poor old lady's discomfort. So this chunk of code needs a name. Here we're talking about a sequence or a chain of events that describes a sort of bizarre food chain. There's a trade-off here. We have taken something that was blindingly simple, and we've complicated it. We've paid a price, but we've also gained something important in return. Our mindless simplicity was hiding information. The complexity of this is revealing the bones of the algorithm. So remember that I've not actually used the code anywhere. I've been doing all this experimentation just as a parallel implementation, just to kind of see what it might look like. So now I feel ready to swap it into the actual code. And this is the first place in the code where the algorithmic bit occurs. And here we're in verse 2. If you swap this line out with a call to the chain method, the test blows up because it generates the entire chain, not just the line that we need. When my tests fail, during a refactoring, the first thing that I do is undo my change to get the test back to green. And this might seem odd to a lot of people, right? It's obvious what's wrong. I could just fix it. Why undo? Here's the thing. I think I know exactly what's wrong, but I have been wrong about what I think is wrong so many times. And when you're right about what's wrong, it's great, it's fine. But as soon as the first fix doesn't actually fix the problem, that's how you get sucked into that vortex that ends with a git reset hard hours and hours later. So some people have a rule, and it goes like this. Your tests cannot fail twice in a row during a refactoring. Now, this is a good rule, but I'm a little bit lazy, so I don't bother counting. So if it blows up, I just back out, and then I make the change. That way, if the fire alarm goes off or if I'm struck with a sudden need to go to the beach and drink Mai Tais, I can safely put my code in production if I need to. I know that it runs. When your refactoring steps are really small, like the ones that we just took, it doesn't even really hurt to throw the change away, right? Usually you're just throwing away a few seconds of work, maybe a few minutes at the very most. And it doesn't even feel wasted because typically you'll have learned something from that change, something that gives you an idea of a better change that you can make. All right, so back in the code. The problem is that I forgot that we don't need the whole chain with all of the critters in all of the verses. Right, we just need the critters that we've introduced so far in the song. So now when we call chain in verse 2, the test passes. So let's look at verse 3. Swapping in chain here fails. It turns out the chain is generating this sequence of events, which seemed right, but actually the original song always throws on some extra commentary when it talks about the spider. And it does this for every single verse where it describes the bird catching the spider. So back that change out again, get the test suite back to green, and let's rethink this. One part of the chain is not like the rest. And what you'll see in most code bases when you have a rule with an exception is a conditional. And now most advice about object-oriented code will tell you to avoid conditionals, and that's pretty good advice because conditionals have a tendency to breed. You start with one thing leads to another, eventually somebody's going to get hurt. But it's not immediately clear what we should do instead. So I'm going to lean into this conditional, and I'm going to see what happens. There are two important principles to keep in mind when dealing with conditionals during a refactoring. The first is that the conditional itself should contain the smallest possible difference. And this may sound obvious, but I can't tell you how many times I see conditionals that have duplication in each of the blocks. If it's the same thing in multiple blocks of a conditional, then it's not really conditional on anything. But then if we keep only the wriggly bit of the spider, then there's nothing to put in the else branch. Now, you could drop it, and under normal circumstances, that might be perfectly fine. During a refactoring, that is almost certainly going to lead you astray. This is the second principle, and getting this wrong could throw your entire refactoring out of whack. A good conditional doesn't represent the exception to a rule. It represents multiple variations on the same concept. The rule is one variation, the exception is another. It's not two different things, it's one single idea. So in the song, we're talking about the critter's distinctive features or some sort of qualifier. It's just that most critters aren't all that distinctive or special. So if you drop the else and leave only the bit about the spider, then if you name it, the concept will almost always be named about the spider itself. Remember that the whole point of this refactoring is to be able to swap in arbitrary creatures. So we would end up with a spider tag that returns the tag for a squirrel, or a crab, or a raccoon. The words we choose are important. A name that is nonsense, but temporary, is fine. But if you have a name that feels right enough, then it's probably not going to go away anytime soon. And if you name a fragment of an idea, it introduces not just indirection, but misdirection. Right? It's a magic trick. It gives you an illusion of understanding. And this sort of deception makes it really difficult to refactor. So by forcing yourself to consider the symmetry of the entire conditional, you're nudged in the direction of thinking about the concept as a whole. All right, so the qualifier method needs an argument. Prey isn't really the right name here anymore. Prey is about hunting. This doesn't have anything to do with one animal killing another for food. It's about the critter itself. And now this conditional feels right. Take a moment to look at it. It contains the smallest possible difference. It's symmetrical, containing both the exception and the rule. The name doesn't misinform. It's about a general concept in the song. Notice that the result of the method depends solely on the argument that is passed. Right? This method could live anywhere. It could be a global function for all we care. It doesn't depend on anything to do with the song class. Earlier in the refactoring, we identified the concept of a critter. Each critter is a string representing the name of that critter. But now it turns out that there's more stuff associated with a critter. Each one also has a qualifier. With our qualifier method, we're trying to decorate our very simple critter with more behavior. And the official name for this code smell is primitive obsession. The remedy for primitive obsession is to identify the object that is struggling to get out. Our critter is not a string, it's an object. And this is the turning point for this entire refactoring. Now, suddenly, it's clear that all the variable bits of the song are associated with this critter object. We can comb through the song, find all the parts that are about an individual critter, and then flesh that object out. And the delightful thing is that in doing so, the conditional just disappears, right? It's very useful to use the conditional to help identify the concept, but once we did, we no longer even needed it. So it turns out there are three things that this critter might have. There's the name of the animal itself, then there's the qualifier, and then finally there's a little bit of commentary from the narrator in the song, which is used in every verse for the animal that is the subject of that verse. So for the sake of refactoring, we can instantiate all of the critters based on the data that we extracted, tweak the algorithm a little bit so it uses the critter objects instead of the strings, and then we can swap the algorithm straight into the verses. So this is the 7th verse, which is the second to last verse in the song, and I chose it because it has the longest chain in it. So it should be a good representative example of the algorithm. In the first line, we need to get the right creature, and then we want the name of it. The next line is the same creature, but we're calling the commentary method on it, which I've renamed aside because it's shorter and it had to fit on the slide. And then this time, swapping in the chain actually works seamlessly, and then the last line is always the same for all of the verses. It's the first critter that we ever encounter, which is the last critter in the list, the one that started the whole cascade of trouble back in the first verse. So at the start of this whole process, in thinking about the task, it felt really useful to divvy it up into roughly 3 phases: how to construct a verse, how to string the verses together, and then implementing the new feature. So we've nailed the first bit. We have a really good separation between the parts that remain the same and the parts that vary. And our code is basically stringing the verses together correctly. We kind of got that one for free. But we still can't swap in arbitrary creatures. And it turns out there are 2 things that are getting in the way. We have a hard-coded constant with all of the data that the algorithm is operating on. And then in several places, we have hard-coded assumptions about how many creatures there are. So the hard-coded constant is straightforward to deal with, so we're going to go ahead and do that first. We are referencing it when we instantiate the critters here. So rather than rely on the constant, we can add a little bit of indirection by creating an initialize method, which is a constructor in Ruby, and then we can inject the data as a default value, which allows the caller to override it if they want to. So we need to store the data, make it available via getter method, and then refer to the stored data rather than referring directly to the constant. And that's it for the constant. So that was 4 tiny steps, and every single step was safe. In the context of a refactoring, safe has a very precise technical definition. A safe step is one change where the code will work both before and after the edit. In other words, if you refactor with only safe steps, then the tests will pass the whole time. All right, so we've dealt with the data constant. Next, we are going to tackle the assumption that there are 8 creatures. This happens in a few places. The first is when we generate the lyrics for all the verses, we create a range object that goes from 1 to 8, which we then iterate over. And this is straightforward to fix because we have an array of critters, so we can get the length of that array. A slightly more resistant problem is the verse method's case statement, which has a single block for each verse. Again, with the assumption that there will always be 8 verses and only ever be 8 verses. So most of these blocks are very similar. The only difference between them is that they hard code the number of the verse that they are in. So we happen to have a variable handy for this. This is I, which gets passed to the verse, which is the value that the case statement is switching on. And once all the verses of the chain are identical, we can collapse them into a single block. And then the two remaining verses happen to also be identical, so we can combine those into a single block. And there is a fair amount of duplication between the two blocks. But I'm not going to worry about that right now. I'm going to just ignore it, because I'm in the middle of dealing with the hard-coded assumptions about creature count. And I want to finish my train of thought before I move on. If you read this case statement, it seems to be saying, if it's verse 1 or verse 8, do one thing. If it's anything between 2 and 7, go ahead and do something else. And what we really mean here is if it's the first or last verse, do one thing. Otherwise, in all other cases, do this other thing. And that's basically it. If we've done this right, we should now be able to generate lyrics with arbitrary critter data. So the simplest way to check this is to write a small test. And when I say small, I mean as small as possible, but no smaller. So the test data, it needs to cover all of the cases, all of the unique things, the things that are relevant about the song, but it should not be realistic data. If you use realistic data, it's going to distract you from what's important. So instead of lions and monkeys and lizards, the data should be really, really simple and contrived and very boring. So with this data, we should end up with these lyrics. The first and last verses are both short. The middle verses are long, and then one of the middle verses has that extra qualifier on it. So if we stick this whole thing in a variable, then we can assert that the code does the right thing, and it doesn't, which came as a surprise to me when I was preparing this talk. It fails because we have the wrong indefinite article, so that's a or an, a zebra, or an alligator. And this doesn't seem like a very big deal, but fixing it in a smart way, it's actually really difficult because English makes no sense. So I'm just going to do the naive thing, which is to add the article to the data array for both the new test and the original data constant. And this will require some small adjustments in the code, but it's really straightforward and only takes a few moments. And then the new test passes. So we've successfully taken a hard-coded string and refactored it into code that reflects the underlying algorithm. And the code is not perfect. There's still annoying stuff like the duplication in the case statement, or even the case statement itself. We could address those things, but we don't have to. Right? The code now lets us do what we need to do. It's simple enough to understand. Kent Beck once said, make the change easy, then make the easy change. Right? First, refactor the code. Change the structure without changing the behavior. Keep doing this until you can add your feature without hacking it in. And often you'll find that implementing that new requirement just takes a moment or two, and it kind of feels like a miracle. Actually, Kent Beck didn't exactly say this. What he said was make the change easy, warning this may be hard, then make the easy change. There is exactly one thing that I hope you'll take away from this talk, and that is to take smaller steps. Now, your steps definitely don't have to be as small as the ones that you saw in this talk, but a good rule of thumb is that the higher the uncertainty, the greater the risk, the smaller the step should probably be. And this process can feel pretty scary, because when working with real-world code, a lot of those steps will feel like they're going in the wrong direction. You'll be pulling logic all into the same place, getting rid of unhelpful abstractions. Along the way, you'll end up with methods that are hundreds of lines long, with conditionals that have dozens of branches. They're nested lots and lots of levels deep. And I'd like to reassure you that that's fine. It's fine to make things worse for a while, to help you get things under control. It's fine to implement gross workarounds temporarily, if that will help you make your changes safely. Take small steps in whatever direction will get the job done. And if you do, refactoring will become delightfully boring, and you will have more bandwidth to focus on the meaningful parts of your job. Thank you.